Hello, everyone. Hi. Sorry, I got a little late today, and yeah, I hope everyone is here. And yeah, I can see some people. Yeah, good afternoon. And let's see. So we'll have a short class today. We'll not be, uh, you know, will not be going. Will not be spending too much time. One is because there is a department meeting that is there where I'm supposed to be at 4:30. So I think we'll finish the class before that. And besides that, I think more or less we have covered the main grounds of the course. Okay, so all the topics that were supposed to be there as part of the syllabus that are covered mostly. Okay, there are a few things that are remaining, and now we can, in the third module, we can take a look at these other additional topics that we had thought about. Okay, so today I think is a good day to discuss things like the limitations of the things that we studied, and uh, whatever we've learned, how much of it is, you know to what extent did we learn things. Okay, so some things like that. So let's first take a look at yesterday's thing. So let me just shift. uh, Let me just shift to that. Yeah, so we did sheet metal yesterday, and I think we covered all of this, right? We covered how things are bent, and we did like a very uh, we did like a very I think we did like a little rushed explanation of all the things, all the processes in sheet metal. All of these, the processes that you see in the slides, they are fairly, you know elaborate if you want to study them distinctly. If you want to know about the process parameters that are there, what are the kind of design considerations that you need to think about, then you will need to go through each of these, and I would suggest you do that. Okay, so what I've done is I've put a few videos on the OneNote shared file. Let's see if I can show you OneNote. Uh, right. So, okay. Yeah. So if you can see, this is the class resources section, and I put in the details of all the things that are there. I forgot to put in the live stream links of the other few days, but yeah, that I will do. And besides that, if you go to each of these pages, there are some interesting videos for you to watch, based on whatever we have studied. Okay, and from yesterday's class I've put in some of these videos. So for example, if you look at this one, let's see, my desktop audio is, yeah. So I've muted the desktop, but this will tell you how shearing operation is done in sheet metal. So what are the details in the shearing operation? Those kind of videos, and some fun videos. One video is there on spinning, which is a very interesting video by one of my favorite YouTube channels called This Old Tony. This guy is super funny, and he really explains some of the practical aspects of machining and manufacturing processes. Mostly it is about like DIY machining, but it's a very good channel, so you can watch a lot of other videos that are there. Then yeah, so if you were wondering where I had shared all those files about the 3D model, this is the one. This is the 3D model. I think this is like a render, and I'm sorry, it opened up in another window. So yeah, I've pasted some videos and all of these things also. Okay, right. Okay, so go ahead and watch all of these, right? And besides that, I've created some of these spaces over here for you to share things. Uh, Somebody put in a question saying, "Sir, would you be posting lecture and highlighted assignments here?" I can do that. Okay, there are some pages for memes. If you want to put in something funny, then you can do that over here. And there's like some interesting materials and things like that. I think this uh, somebody else pasted, and thank you so much for this. It was quite interesting. I had seen this video, but it is genuinely interesting. Okay, and these ones are about shape memory alloys and all that. So if you think there are some interesting videos that you want to share with others, then I please go ahead and paste it over here. This will become a very good repository for other later batches also. Okay, so anyway, so this is like the OneNote file. Okay, so we discussed all of this, and right, okay. So yeah, I am seeing some comments. Chaitanya is asking meeting to get us back on campus. I don't think so. No, you are not coming back on campus very soon. So or anytime soon. I think maybe next year sometime, April, May, June. Whenever this whole pandemic situation gets over. Yeah. So anyway, so today we are going to, let's see. I wanted to discuss this. Yeah. Don't worry about the day 6 part. It was from an old presentation. I copy pasted the slide. So this is day 9, by the way. Okay, and yeah, yeah. About coming back on campus. Yeah, maybe. Hey, don't quote me on this, huh? This is my guess. That I'm guessing. I think so. Maybe I don't know. Yeah, there's a lot of you know unsurety with this whole matter. But people are working towards it. Let's see when they find out. There'll probably be like proper official communication from IIT side. And yeah, don't quote me on this. This is just my guess. I'm guessing maybe. Okay, a little pessimistic guess, if you can say so. Okay, so yeah, don't worry about it. Okay, schools, Chetan is saying schools open today, so hopefully college will do so. Hopefully, yeah, if that happens, then I think it will be like a little bit of an emotional relief, but then people have to really think about what is the implication, health and safety implications. So those things are paramount for everybody at IIT. All the administration really cares about the students. I should go to this bigger one. Okay, so since we are not talking about the course, yeah, everyone at IIT really cares about how you want to uh, you know how to keep you safe and all that. So it's very important for them, so they are thinking about it. uh, but yeah, I mean, I don't know. I have a feeling that this whole pandemic situation is probably going to go over till April or something. At least, I think there was a recent communication, if I'm not wrong, from IIT side that next semester, I mean, like next semester, the first year is going to be online from, I think, November onwards, maybe, or something like that. So we'll see. So I don't think I'm the right person to answer these questions. I really don't know. Uh, the best person would be our HOD. So I suggest you can kind of, talk to him and get your clarifications. Yeah, the Amir, the professors do miss you. Not you in particularly, but like all the students. And it's quite dead without the students, right? So yeah, anyway, Forget about all of these things. Let's get back to what we are here to discuss. Okay. And okay, so let's start off with this slide. I mean, this is like a common slide just to give you the perspective of what we are discussing and where we are. We had already discussed a little bit about, let's say, about manufacturing processes which particularly, you know, consider liquid material in the liquid phase, and we discussed all the operations such as forming and extrusion and forging, these kind of processes where which use materials when they are in a plastic phase. So they manipulate material which is probably in this state. And finally, we also discussed a lot of processes which consider materials when they are in a solid state, like machining. Most of the machining operations are like this, and even for some forming operations, sheet metal operations will consider, you know, material in the solid phase, right? So today we are going to talk about something that doesn't lie in this spectrum. Okay, that doesn't lie necessarily in this spectrum. Okay, so let's, and yeah, we I think I showed you this slide before. So today we are going to talk about something called powder metallurgy. Okay, so this does not lie in that spectrum. Okay, if you want to put it in like in one in that kind of a chart, it does not lie there. So the idea is that in this particular manufacturing process, your end goal is, of course, to make some parts which are like these, let's say, like gears or so, things like that. And the starting material is powdered metal. Okay, or if you zoom in really close and if you look at it under the microscope, or then you'll see like beads of metal. Okay, metal particles. So this is powdered metal. Okay, and using this, such things are made. So you can already kind of guess what would be what could possibly be the steps involved. Okay, one process we already spoke about. So one of those processes was metal injection molding. So what you could do is, this powder you could mix it up with plastic, and you could pass it through an injection mold. You could mold the part that you want, then take it through the necessary chemical paths, and put it in an oven to remove all the plastic, and and then one of the processes that we discussed was something called sintering, which basically the idea was that after the plastic has been removed from such an injection molded metal injection molded part, the sintering process heats up these small granules of metal and melts them just enough so that they can fuse together and form like a homogeneous solid part. Okay, so those similar processes are taken forward in powder metallurgy, and let's discuss what we see. Okay, right. So first and foremost, like the schematic diagram, how does it look like? What are the processes that is done? So first is, you have to somehow make metal powders. Okay, and there are several types of process. Not all of these are processes for making, metal powders, but this one, for example, atomization is a process. Electrolytic deposition is a process. The others I am not very sure. I don't know what carbonyls are. I haven't googled it yet. So yeah, maybe you can do that. Okay, so somehow you have to make metal powders. Once the metal powders are made, you have to you can add a few things into that metal powder into that powder, and you blend it to make like a homogeneous thing. Why do you do that? So for example, in this case it says add lubricants. Okay, so the idea is that naturally, to reduce friction between the surfaces of the die and this metal powders, you probably add a little bit of lubricant to the whole mix. Okay, you can add other kind of additives as well in this stage, right? So when you blend it, and then there are two directions that you can take. You can do something called hot compaction, which is you put the metal powder in a cavity, in a die, and you heat the whole thing up. Okay, you ensure that the whole this whole blend, this blend is heated and pressed together, and typically the process of pressing, okay, it's since it's fairly complicated, no? So now that you think about it, let's say if you just want to make a glass also, a water drinking glass, then think about how you would press it, right? So it will be quite difficult to do something like that. So there is a process called isostatic pressing, which uses pressure, okay, pressurized gases, or inert pressurized gases, or in some form of other fluid, pressurized fluid, to press the powder into the right shape at an elevated temperature. Okay, so that is hot compaction. So similarly, there will be something called cold compaction, where you can use several other processes. Let's say you just want to make like sheet using, or some part which is in the form of a sheet, okay, or flat in that manner. Okay, so you could use something like rolling, or you could use some isostatic pressing similar to this process, but in without temperature. You could also extrude it. Let's say you blend it with some kind of materials which help you retain the shape of that blend. Okay, so you could extrude it, and you could also injection mold it, just like in a metal injection molding process. So this way, metal injection molding is also a powder metallurgy process. Okay, now after in hot isostatic pressing, what happens is that the temperature, since the temperature and pressure are applied together, what happens is the granules get sintered, or the granules kind of homogeneously mix together in the same single process, and then secondary operations, anything which are required, like finishing and making holes in the right places, and other kind of processes can be done, like coining, let's say forging. They've just given some examples of what kind of things can be done. On top of that, you could also do some form of heat treatment to, let's say if you want to make the part, that powdered metallurgy part has a harder surface, then you could do some heat treatments to get those properties. Okay, whereas let's say in cold compaction, what happens is that you are doing the action of pressing and heating separately. You're dividing those processes, right? So you need this one more process which is called sintering, and typically it could be done in normal atmosphere, or it could be done in a vacuum, to ensure that no added impurities are added into that mix while it is being heated. There's no oxidization of any layers on that part, right? Cold compacted part. So this is like the schematic diagram overall. But if you look at like the actual how the industrial processing of this whole thing happens, and if you look at it from the series of machines through which material travels through, then you can understand the sheer scale that is required and the complexity of these kind of process. Okay, so this chart kind of gives you that. Okay, so you have different types of powders that you can make from base metals. So for example, aluminium, you can make some kind of powders using aluminium, some from iron, and all other things. Now having this in separate powder form makes it much more easier for the engineers and the production people in production to accurately mix the different metals and different compositions together to get certain properties, from the final part. Okay, so you could say that it's similar to an alloying process, right? So in an alloying process, in the crucible where the metal is heated and melted, you would add these different materials, right? So in this case, however, you would do it in the powdered form. So naturally, with these powders, some lubricants are added, some alloying elements are added, and it is mixed homogeneously. Okay, then that goes into a forming machine, which where, let's say, the basic part is made, okay, using pressing. So here, for example, uh, so let's say this is the die, and there's a top and a bottom part, and then that is pressed, and you, once it's injected, you get this kind of part. Sorry. So that kind of goes and travels through a sintering, oven. Okay, and once it goes through, it is heated, and when it comes out, then it has whatever unnecessary, whatever things that were like binding agents or anything like that, those gets evaporated out. The little balls of metal at powders, the individual balls kind of melt because of the heat and fuse together to form a more homogeneous part. And then if that you could use like a secondary process of repressing to ensure that the material, you know, the part that you want is in the dimensions that you want. Okay, so you could do the sintering process in stages. You do one pass, you reform it to get it a little more accurate dimensions, and you resinter it, and so on. So now, going down the line, what happens after this comes out of the sintering oven? The part is mostly finished, okay? And you would first, naturally, you would remove any burrs. So burrs, sorry, burr, burrs are these sharp edges and sharp corners and the flashes that come that happen when these parts are formed and made in these machines. Okay, so those are removed. Basically, it's a cleaning process, and once that happens, you could take it through different processes as required by the in for the part. So for example, you could take it, let's say, and you can weld it to some other different part, right? So you could use some joining operations. You could machine necessary features into that part. Or let's say after the sintering has happened, the part sizing is really not there, or you had chosen like a multi-step sintering process, in which case final sizing you could also do. Forming operation, this is another form of forming operation. And then after that, you would do some treatments. Okay, you can do some electroplating, like let's say you could plate it with nickel or chromium to get a very shiny outer layer. There is some processes where resin or oil is impregnated, especially in parts where which need to function in an oil bath. Okay, they are constantly washed with oil. No, generally it's a good idea to ensure that the part has absorbed some amount of oil. Okay, now this is very like a it's a non-typical, it's not done very typically in most of the parts, but some applications require that to happen. Okay, and resin impregnation is basically, let's say, you can imagine, since part is made out of the small metal balls, there is going to be some amount of very fine gaps in between these balls. Okay, you could design it like that also. So you could design it to have some gaps between these different particles of material, and when you can push resin into those parts. Okay, and that probably makes the part much stronger. So that is possible, right? And you could do some steam treatment, and you could do some heat treatment, and you would get the finished part. So this is kind of the production line of the whole thing. Okay, it was a very interesting diagram, so I thought I would share it with you. Right, so naturally the first question is, how do you get powdered metal? Okay, so there are these three or four processes that are there, three processes that are there, which has been shown. The first one is a very interesting process where you have a device, an interesting device of this kind of a shape. So this is just the schematics, of course. So this kind of shape where molten metal is poured in from the top. As it flows down, as the molten metal flows down, water is sprayed onto that molten metal, and this is quite cold water. And uh, because of this process, right? So metal particles are formed and they get deposited down. Okay, so it's almost like spraying molten metal. Okay, if you spray molten metal, you get the small particles of molten metal that you will rapidly cool, and you ensure that metal particles are formed. It's a highly process. There are so many process parameters that you need to control, otherwise you may not get the right sizes of metal balls and all that. Okay, sometimes you can do this in like 2 or 3 operations. So you make like slightly larger versions of these metal particles, and then you crush them. Okay, you can crush them under through various means. Okay. The other one is something similar where you would have, okay, so you have like a non-rotating tungsten electrode. So there is a tungsten electrode here, and from the other end there is a rotating. So this part, this small black triangle that you see, that is a rotating consumable electrode made out of whatever material that is there. And there's a, so this whole thing is situated inside an inert chamber. So first whatever air is there inside, that is removed. Okay, and then inert gas is added, so that it becomes so it the atmosphere is devoid of oxygen. What happens if oxygen is there? Chances are that the metal is oxidized, and you'll get rust instead of, let's say, iron particles if you want to make. Okay, so what happens in this situation is that there's an electric arc which is created, which kind of hits the metal or hits the metal and burns away some surfaces. Okay, so yeah, something like that happens. And these three are more mechanical processes, and here, for example, it's very simple, like crush the whole thing between 2 rollers. And here, this is like a large drum where you put metal and some material which would crush the metal slowly. So you would rotate it, and over time you would get metal powder. So similarly, this is also a crushing method of crushing. Okay, so these three are more mechanical processes. So this is how you would get metal particles. Right, so now the next step is to compact the whole thing, and the idea is that this is one way. This is die compaction. Okay, and die compaction, what you would do is, let's say the powder is there and there is a certain kind of die shape, and it so let's say you want like a cylindrical pipe kind of a shape. Okay, and you press it between two dies, and there are some arrangements which would, like this ejector, these kind of things, right? So this gray part that pushes the part out when it's done. So here you can imagine this as a 1, 2, 3, 4 step automated process, where powder is kind of taken from one end, pushed to the right location. This cap, this dark red cap that you see, that is removed. The powder kind of fills into this location where there is a gap. Okay, and these two die, top and bottom, kind of push down, and this whole thing is compacted. So when it is compacted at the microscopic level, what happens is that these balls get kind of crushed together, and they are held together by the binding agent that is put there, and the just by the frictional forces in the whole thing. Okay, so this is like another example. So you have this die, there's a lower punch, there's an upper punch, and these are serrated so that you so for example, this one particularly is used for making this type of gear. Okay, it's a spur gear, and it has a custom central axis shape. shape of the central axis is slightly elongated, and so machining this would be slightly, or it's not because of machining, but let's say you want uh, okay, I'll come to that. I'll come why powder metallurgy is better slightly later. So the same thing, you can imagine this setup over here. So this red is the die. Okay, the powder comes in, it fills into the right location. This is the lower punch. Okay, you see the lower punch. This is a core rod which is used for this particular hole that is there, and this is the upper punch which comes in, presses together, and in this shape the powder is compacted. Okay, and I'm sorry. So, and then what you do is you do something, you do the compression. So there are two processes. One is hot isostatic pressing and cold isostatic pressing. Okay, so the first one, let's say cold isostatic pressing. Okay, and the idea is that you whatever part that you want, no, you build a shell inside which the powder is filled. Okay, the shell is designed in a manner that it, once filled with powder, the internal cavity, where the powder is held, is in the shape of the part that you want. So here in this case, let's say the green one is the powder that is there, and this shell is made, the blue part. Okay, and there's whatever cores or whatever things are there, and there are stoppers, and this whole thing is put inside a chamber, and the whole chamber is pressurized. Okay, because of the pressure in the chamber, the all these parts experience a force along its surfaces and uniformly throughout. Okay, and that is held for some time, and once that pressure is removed, this is kind of compacted, the part is compacted. This one is an idea about hot isostatic pressing. So this chamber is here. So first what you would do is you'd make this kind of a shell. So the shell is probably made out of sheet metal. Okay, mostly it is made out of sheet metal. In that sheet metal shell, you fill in the powder and you ensure that you remove all the air and whatever impurities that are there using vacuum or some other method. Okay, and then this whole thing along with the shell is put inside an oven, hot isostatic press, where temperature is applied along with the pressure, let's say, just as in this case. So naturally you can imagine the complexity of this such a machine for doing hot isostatic pressing. Okay, and then finally so this example kind of tells you to how the pressure and the temperature changes over the cycle. So you would increase the pressure, you would increase the temperature, you would hold the pressure and the temperature at a certain value for a certain amount of time, then you would start reducing the temperature and the pressure after some time. Okay, and then once that is done, the part along with the surface, along with the outer casing, that whole thing comes out. Now the outer casing, you can remove it maybe by machining, or there are some very simple methods, like if you made the outer shell with, let's say, some specific material, you could dissolve it in acid, and the internal part itself doesn't dissolve in acid, so you could design it in that manner. Okay, so the schematics is fine. So I found this very interesting video, and let's see, it explains hot isostatic pressing, and let's see the video. First I would like to add this thing. Okay, so just a second. Can you hear? Just tell me if you can hear.
Welcome to Sandvik, a world-leading producer of near-net-shaped products produced by hot isostatic pressing, or HIP. HIP solutions offer many benefits compared to traditionally forged or cast products. Complex geometries, no pores or weaknesses, and short production times are just a few. HIP products for offshore operations, power generation, and other applications can be produced in a wide range of Sandvik grades. The manufacturing of metal powder for the HIP process is based on controlled quality scrap and alloying materials. Melting takes place in an induction furnace. The chemical composition of the melt is closely monitored through.
So it starts off with like a typical alloying process. In this case, let's say they use an oven to, here they are saying induction oven, but you can use basically any kind of an oven which is enough to melt the material. Okay, so you would add whatever material composition that you want to get the properties, the alloy properties that you want later on.
Throughout the process and adjusted to meet Sandvik requirements and international standards. The powder is produced by blowing inert gas through the melt, which solidifies into small spherical metal droplets. Rapid solid.
So as you can see, the schematic that we showed in our images also, it's something similar. So you would pour molten material and a thin stream of it is passed through at one point, and here they are using inert gases naturally, because inert gases would not oxidize the material. Okay, otherwise, let's say if this is steel, then it would rust, and the whole thing would not be suitable for the use.
Solidification of the melt produces a metal powder with a fine-grained microstructure. The metal powder is collected at the bottom of the atomizing tower. To ensure a consistent and homogeneous powder quality, larger particles are removed.
So, doing this directly is not as easy as it seems over here. Okay, it has a lot of process parameters that needs to be controlled if you want to ensure quality metal powder. Okay. Now
manufacturing of the finished component begins with the design of a capsule.
So here he's saying it's a capsule. So what I said shell, no? So here he's calling it as a capsule.
According to the required near net shape of the finished product. The ability to.
So near net shape, the word near net shape has come in quite often in our presentations, and the idea, what is a near net shape, is that let's say the final part has a lot of screws and holes and whatever is required to assemble the part, right? So you remove all of those features which can be easily made with other processes, right? So they need not strain one process altogether, even if they can possibly be done. So you remove those features to get a overall shape. The choice of the near net shape depends on a lot of things. One of the key things, besides the cost and production constraints, is the stresses. So you shouldn't whenever you are designing, like let's say you are making a forged part, the near net shape should ensure that whatever features come under a lot of stresses, those features are properly thought about, and they are not something which are removed without consideration from the near net shape. Okay.
Manufacture HIP products with irregular shapes and complex geometry offers several advantages compared to castings.
So you saw this is like a sheet metal shell made out of various parts welded together, and these kind of weldings need to be also perfect because of the process that is done later on. Just
forgings. The capsule is made by forming and welding sheet metal. The tightness of the finished capsule and its welded joints is verified by testing with helium gas.
Okay, so what happens is once the capsule is made, helium is passed through the whole thing to ensure that there are no leakages. Okay, now why helium is used? Because it is an inert gas. You could use hydrogen, which is much smaller than, or slightly smaller than helium, and it would probably give you a little better results. But hydrogen is an explosive gas, right? And so helium is used, and helium will find any cracks that are there, or any micro cracks, even if the surfaces. Sometimes what happens is, due to impurities in manufacturing of some sheet metal part, maybe some holes, very fine holes are there on the surface, which cannot be found through other means. Okay, so helium penetration test is a test which is done to find out these kind of leakages.
The capsule is filled with metal powder according to a pre-calculated weight. The powder is packed by vibrating the capsule. After filling, the capsule is again tested for tightness with helium gas.
Okay, so two
The
stages
filled
they
capsule
do.
is evacuated and inserted into a cylindrical hot isostatic press. This is where the hot isostatic pressing process begins. To obtain 100% densification, the capsule is exposed to high isostatic pressure using argon gas and applying high temperature. The volumetric shrinkage during the HIP process is approximately 30%.
Okay.
The HIPed material
So that is an interesting technical information that he provided. The overall volumetric shrinkage is around 30%. So you need to design the parts in a manner that, so for, let's say, this kind of manufacturing process, you would need to scale it up and then make all of these shells and whatever is necessary. Okay.
is heat treated in qualified and approved furnaces to obtain correct properties. Rapid cooling is important for many materials to ensure the required properties are attained. After heat treatment and removal of any test material, the part is pickled by submerging the capsule in sulfuric acid, which dissolves the sheet metal. The HIPed material undergoes destructive testing to verify
This
pickled by submerging the capsule in sulfuric acid.
So here they are using sulfuric acid. They've chosen the material of the outer shell and the powder itself in a manner that has sulfuric acid dissolves the outer layer of the whole thing. Okay, you could control this to ensure that the sulfuric acid dissolves the whole layer to a certain thickness, very, very accurate. Okay,
which dissolves the sheet metal.
then you
The
do
HIPed material undergoes destructive testing to verify strength, toughness, corrosion, and structural properties. The final product is fully inspected for defects using non-destructive ultrasonic and dye-penetrant testing methods, as well as ferritoscope and positive material identification. The geometry is evaluated by laser scanning after the HIP process and before machining to verify that the product meets
So these processes of laser scanning and verification, although they are done mostly by almost all industries, they are not specifically, need not be done in this particular manner also. There is a very interesting machine called CMM machine, which is used to verify the dimension of parts. Okay, dimension of parts. It's a computerized measurement machine or something. I forget the full form. The CMM machine.
dimensional requirements. The uncovered product needs no or only minor machining, since the hot isostatic pressing process results in a near net shape component. The product is ready for delivery, accompanied by certificates and a
So as you can see, so from that near net shape, this kind of final part is delivered, where you would have these machined holes and all these kind of chambers and all that. put in later on. Okay, this were not there in, although this could be done in the directly in the HIP process, but it would increase the complexity of the, you know, the encasing to a much higher degree. Okay, so to reduce that and to reduce cost overall, you would do something like that.
Complete documentation package. Sandvik has now fulfilled its commitment to produce and deliver a powder metallurgy product of superb quality, capable of operating in the most challenging environments.
Right. So there are other videos in the slides which I will leave for you to watch later. And let's take a look at what exactly happens at a more granular scale when it is sintered. Okay, so when it is when the green part or the compacted part comes out and then put in a sintering oven, this is what happens. So first, when you press it together, there's the, because of the large pressing forces, some amount of metal has diffused, very small amount of metal has diffused towards into each other. Okay, and then after that, so once it is heated, these kind of processes start taking place. There is a neck which is developed. Okay, and yeah, so and then finally this kind of bridge is created between powders. Okay, powder particles. Okay, so what are some of the design considerations that you need to do, need to think about when you are thinking about, let's say, powdered metallurgy parts? So first and foremost, like sharp edges, it's always difficult to do this. So it's always a good idea to have some fillets. Okay, similarly, sharp radii, instead of that you have filleted, although this can be done, right? So rather you opt for this. Okay, if there are something like this, then the near net shape, which will be made out of the processes, powder metallurgy process, should not have this, and you should consider making this later on in the machined operation. Okay, however, this kind of thing can be molded. Why this can be molded and this can't? Because let's say in this case, no, the way in which this will be molded, this will side from, so let's say this will probably be the parting line, and this side will represent the shape of the dies. Okay, or probably let's say if the parting line is over here, whatever, so the die will move one this way, one that way, right? And because of that, if such a configuration is there, these small areas will become undercuts. Okay, whereas that is not a problem here. So let's say if this is the parting line in the part and the die moves one this way and the other this way, then the die can easily come out from this kind of a groove. So it is possible to have this in the mold, but like an undercut is not possible. Okay, or rather needs a lot of jugglery. So rather have it in a machine thing. Similarly, you can have, if let's say you want to have a hole drilled, so think about drilling it rather than having it as a part in the powder metallurgy thing. Similarly, threads, if you want, you can make it using machining. So since the schematic, let's go back to the schematic of this. So since this is this overall schematic, you can imagine that this needs a certain amount of consideration. So it doesn't need draft angle per se, because you are pushing it from the mold using this ejector pin. But if there is small draft angles, then it will be much easier for the ejector pins to push this thing out. Okay, so let's say instead of let's clear this out. So let's say this part, since it is being pushed out by this ejector pin, then it's a good idea to have it in this shape. And Okay, I'm exaggerating the whole thing, but let's say the central ejector that is there, this one, the blue one, will probably come to this, height over here, whereas uh, the this ejector pin will kind of push it from this side. So this surfaces needs to have a draft angle like this, so you'll get a part which is something like this. So totally straight part, although possible, definitely not recommended. Some amount of draft angles is a good idea. Now because of this configuration, you can imagine, I can't have a cut which is like this, I can't have a design feature which is like this, because the ejectors and all that will, the punch and the ejectors will latch onto these kind of locations. Okay, so yeah. Okay, so very strangely, although this thing looks like it is a very new and advanced kind of a process, the starting of such a process actually happened quite long back, around 3000 BC. And so the best part of this is you can control it in a manner that is not possible with other kind of manufacturing processes, because each particle you can have some alloy as an alloy, right? So you can have a part made out of multiple alloyed materials also. Okay, it will depend, there's some compatibility that you need to think about, but it is definitely possible. Okay, it's relatively an easy process. There are lesser restrictions in terms of the let's say if you are doing it with the HIP, then there are a lot of the restrictions of undercuts and all of these things go away, because you could wash the outer casing in an acid bath, right? You could remove it like that, so without any reason for undercut. So these kind of draft angles and latching on problems that will happen. It's cost effective, and the problems with these processes are powder metallurgy processes, that porosity cannot be totally eliminated. If it's the final product will be of 80%, around 80% density, and the parts which have not been sintered yet, they are very brittle, and the handling of it needs to a lot of care. Okay, and it says needs large, but needs large investment is what is supposed to say. Right. Okay. Okay, so that does it about for our powder metallurgy section, and we are almost clear of our prescribed syllabus. There are a few things that I think in this class we can discuss. So I would like to discuss three things. Okay, one is additive manufacturing. I think you just know, nowadays it's like become a common knowledge, right? So additive manufacturing has become something quite common. Additive manufacturing is nothing but 3D printing. Okay, or it shouldn't be called 3D printing all the time, because it's not really printing. Any process where you are able to place, or you are able to build the part using one layer at a time. Okay, by adding one layer at a time is an additive manufacturing process. You add things. So you could build the layer by welding. Okay, so you have a base plate, you weld one layer, and then you weld another layer. So any way of depositing or adding material is can be considered as an additive process, right? So, and then additive manufacturing is, if you have the right kind of control systems, then you can build anything layer by layer using additive manufacturing process. Okay, so okay, I don't want to go along these sides, because I want to keep this, we'll discuss this in the next module. Okay, So yeah, I think you have seen additive manufacturing in the desktop scale. It is a fairly recent phenomenon considering the knowledge that has been around, right? So the knowledge about additive manufacturing is not very new. It starts off around 1960s, 1980s properly, okay? And it came to the hands of DIY manufacturers or small scale manufacturers fairly late, around, let's say, I don't know, was it around 1990s or 2000s? Around 2000s is what I'm guessing. Okay, around 20 years back. That's fairly, uh, you know, fairly recent. Okay, and now that the scale of the machines are smaller, earlier these kind of processes used to be really cutting edge and for a lab scale, for a very large company, very niche kind of production process would be there. But now you people make like small toys at home using these kind of processes, right? This has blown up into so many things, like which has changed our cultural landscape, okay, if I may say so, right? For example, there are, there's a considerable ethical concern about making firearms using such kind of processes, where, and simultaneously there's so much, a hope that about these processes, because people are able to print organs, okay? So like kidneys and all these kind of organs, they are able to do using something called bioprinting, okay? And it has come down to fashion, okay? Fashion accessories are being designed. In fact, people have designed entire clothes out of this thing. Medical science has benefited out of this thing. So this is like a titanium jaw which has been, so everybody's jaw is slightly different. So let's say if somebody has an accident where there's a need for replacing a significant part of the bone structure, then you could do like a scan of that person, and that whole process can be followed, where an artist builds a 3D model specific to that person, and those things are printed out and then used as implants in the body. So that has been done, and it's and this one is like a very famous case study. I don't know if you've seen it, but this guy was a industrial designer at Apple, and uh, he came out of that company, and he is, what he's doing is he's making these prosthetic legs which are quite uh, different looking, okay? He's following a very industrial design approach, where his legs, his prostheses do not look like machines, okay? They look like sculptural objects, and they look organic. And he uses 3D printing in an extensive manner to create custom pieces, okay? So it's very, very interesting case study. I want you to search for it, and if you find a good video and good resolution, good quality video, please share it in that OneNote link. Aditya is saying C Zinger 21C. I don't know what is C Zinger 21C. Can you write a little bit more in the chat box so I can see? Okay. Yeah. And as Chaitanya is saying, of course, they are doing full scale building 3D printing. Like, for example, this is a concept model where a 3D printer on rails, on a large scale rail, is kind of depositing, concrete through nozzles and building up these kind of structures, the whole home. Food, chocolate is like very, very simple, okay? And in fact, the scale of it is like so vast, right? So think about this one is like a whole house, and this is an image taken from a scanning electron microscope, and these layers are so tiny that it is difficult to see the layers even through the microscope, okay? So you can imagine this is probably 10 nanometers or something like that sizes. I don't have the scale here, but yeah, well, That's the size. So the variation in size and the scale is also quite astounding. Okay. What is this video? I want to see. Yeah. Oh, I have the video. Hey, good day. I forgot that I had the video. So this is quite interesting. Okay, let's see this.
Wonder what would happen if an industrial designer had to go at making prosthetic legs, things that are beautiful but don't try to look man-made.
Look at this. Just look at this. Right? So, yeah, that's what a designer does. Yeah. Anything that you touch, no, you need to bring in that reason for it to exist in the human world. Okay, and yeah, I don't want to get philosophical in this class, but yeah.
My background is originally from a machine shop. You know, I like making stuff with my hands. Then also I have a degree in industrial design, so my other love is really making beautiful products of all kinds. I worked at Apple back in '93, and once you go through the Apple world, you've really drank the Kool-Aid. You know, from that day forward, you really can't do anything that you're not absolutely obsessively proud of. I had my first exposure to 3D printing 20 years ago, and we probably created some of the first products ever created 3-dimensionally printed. I happened to run into this guy, Ken Trauner, and he was an orthopedic surgeon, but he has a nose for innovation.
Just
so
look
we
at
explored
that.
all the
Look at how this thing. See the knee joint. No, although there's a lot of research going on at IIT Guwahati in the mechanical engineering department by Professor Kanakraj in the mechanical engineering department, where he designed 3D prosthesis, right? So he's designed the knee joint, a low cost knee joint, and the knee joint might seem like a trivial thing. It's like a hinge, right? So directly it's just a hinge, but it's actually not. If you go into the intricacies of it, the way the knee joint works is that the center of rotation, no, it changes, it moves. Okay, depending on the position that the leg is in. So in one position probably the center of rotation is static, and as it goes on, it changes. So you can imagine that the leg is something like this, right? So imagine this is the leg, right? So once it folds, let's say for a certain duration, the point of rotation is quite close to the point where these two are joining. But as it goes down, because of the volume of the leg itself, these things are pushed apart, right? So the center of rotation of these two kind of move, right? So that makes it a fairly complicated problem in terms of just kinematic design of these links. On top of that, throw on top of that the whole thing about it being able to withstand the weight of the human body. That is number two, right? On top of that, throw in the complexity of the human gait, the way humans walk, and everybody's walk cycle is slightly different than the other, and everybody puts in slightly different weight, or the way they put their weight on their feet are slightly different, and in the whole gait pattern, it has to move like a dance. This whole knee joint moves like a dance. You put one leg, and then when the other leg is mid swing, right? And when just before it touches the ground, it's kind of slightly straight. Okay, so if you want to know more about the how humans walk and what is the human gait, there is significant amount of research just in that, and our professor Sogata Karmakar is working. I mean, he's done some work related to that, I think. Okay, and our ergonomics team, professors from our ergonomics domain can help you out with that. So it's a very complicated thing, and that is visible in this. Okay, you see how this thing moves. Let's see.
Has a nose for innovation.
Okay, you see there are two or three parts which kind of move one after the other.
Door for a lot
Okay.
of problems that orthopedic surgeons have. The person who comes to us, they already have a prosthetic leg that's working, and it looks like it was created by a bunch of engineers because it was created by a bunch of engineers. So we said, okay, let's just see what we can do. We three-dimensionally scanned the body, modified things on the computer, 3D.
So this is a scanning process where light is thrown onto a certain surface, and this fringe pattern is thrown on the surface, and that is recorded. Okay.
And realized, wait, we've got something here. We can actually take it and run with it. We started, I think, with 3 people just to test the concept out. And this woman, Deborah, she lost her leg in a motorcycle crash. And we created this fairing for her, and the whole idea was just how beautiful can we make it? Polished metal, 3-dimensionally printed lace-like pattern. Really
Just look
capturing
at
the
that, yeah.
really beautiful calves that she had. And all of a sudden she started sending me texts about people who would stop her in the grocery store and tell her what a cool thing she had. And she was wearing skirts that she hadn't worn to opera.
So you can imagine the impact of good design that it has on the lives of the people, on the there are so many things that I could say about this. Yeah, it's an amazing industrial design
Out in
project.
public so that she could actually show what she had. We were working with Chad, was another guy, lost his leg to cancer. And we created this cool leg for him, one for playing soccer. He's a competitive soccer player. We created another just for wearing around town. And when we put it on him, I think 2.5, maybe 3 years ago or something, he reached down and felt this leg, and he kind of paused. And he said, wow, I haven't felt that shape in 8 years. And that was this amazing thing, because it wasn't just that we're creating something that looks cool.
Just look
We're
at that.
recreating a sense of self. And I think there's this huge opportunity to turn those into not just something that is a engineering artifact that happens just around the body and augment functionality, but really create something that connects to the person, not just in that tactile, physical way, but emotionally. It kind of changed these people's lives, and it changed the way they got through every day.
Amazing, yeah? Yeah, okay. So you can find out and read about it a little more. Right, we will stop here, and there are a few slides after this, but I don't want to explain it because it's like so this is about rapid tooling. So let's say if you want to make plastic parts, how would you do that? And it's a kind of like a small shop process. It's not a production process per se, but yeah, so these things are there. So if you want to look at it, you can go through it. The visuals are fairly self-explanatory. And finally, there's another video that is there. I don't want to share it right now at this stage, and because it's another world of manufacturing itself, and this thing is too very close to everyone. Okay, let's see. Because it talks about how things are done at a very, very micro scale, and MEMS is the full form is micro electromechanical systems. Okay, so and the way it is done is fascinating, and I want to go. So I think there's a video here, so you guys go ahead and check it out later. And yeah, so I think with that we can finish today's class, and mostly I think we've covered everything. And now there are so I'm supposed to give you 2 assignments for this module. So one I'll give you tomorrow, and today's I want you to introduce you to an assignment. Okay. So before that, what I want to do is I want to give you a small tutorial. Are people here in the chat? Are you still watching? Just okay. I want to open Fusion, and I want to show you a few things. Okay. Give me a second. Right, so if people are watching, yeah, okay, good, mother. Yeah, if people are watching and listening, just say hi again. Okay, because what I am going to do is I am going to tell you a little bit about fusion again. Okay, good. So as soon as fusion starts, I'll kind of shift to that. And what I want to do today is give you a little bit of tutorial, a little bit of taste of another kind of domain within fusion, within the whole software, so that you can do the assignment that I want you to do in a better manner. Okay. Okay. Right. Fusion is something using sheet metal. Okay. Conditions. There are two conditions. Number one, there should be at least two parts to the box which should be joined non-permanently. By that I mean that you can understand it very simply, like, so if it's a box, it should have like a lid. Okay, but I'm not calling it a lid. Sometimes you don't want a lid, but I want you to design two parts which assemble together to form in a manner that is non-permanent. The user can open it. Okay. Number two, second condition is that it should be should have at least two parts which are joined permanently. Okay, so somehow you have to think of a way to join these two parts permanently. Okay, no, not these two parts, these two are different parts, two more parts. Okay, so at least there should be, that means three parts. So two of these parts are joined non-permanently, that means they can be removed by the user. I should write that, i.e. it should be for the user to remove. Okay, sorry. Right, so without tools, so that means at least there should be three parts, two of them joined permanently and two of them joined impermanently. Okay, right. uh the box, now here it becomes vague, should have some meaning. Did you do a box, did you guys do a box assignment in the first semester? Just tell me. Yes, you did, right? So this time around, the naturally the box should have some meaning. And finally, here's the big one. So what I'll do is I'll make like a very large this thing. Do a drop test from height. Okay, you could do a drop test in so Fusion 360. It's possible to do simulate a drop test. Okay, use So I can do smaller than this. Use same material as last time, 20166, 2014T6, AL 2014T6, okay, and 8 mm thickness sheet, okay, right? Okay, I think we can reduce it. Let's do 0.67, okay. Okay, so this is the assignment. And finally, so naturally what you have to submit number 1, CAD files. Number 2, render. This time you have to submit renders, okay. Number 3, rendered images. Number 3, results of the drop test, okay. That's it. Okay, so this is the assignment 7. The reason that in this in the past assignment you had to model a chair and do the stress testing, right, on the whole thing. So the reason it was divided into 2 different this thing is because the modeling part was quite difficult. In this case the modeling part is fairly simple, okay, because it's sheet metal, okay. 6 meters. You know what? Let's do 10 meters. Okay, 10 meters high. Is it, yeah. Is this the right spelling for meter? I'm sorry. Okay, 10 meters height. Okay. Yeah, so this is the assignment for you. Okay, so yeah, so that's the assignment. Let's jump into Fusion and let's see how to do. So this is the sheet metal. So first you've got to this design workspace, and there you have solid and surface and sheet metal, right? So sheet metal has specific tools specific for sheet metal. So here, so let me just create a sheet metal design. So naturally in Fusion what you do is you start off with a sketch. So you sketch, let's say in the bottom plane, and I'll press S and I'm going to sketch a simple rectangle like this. Let's give it a dimension. So let's say this is 60 mm. So by the way, I have not given you the dimension for this. You can make it as large as possible, or don't make it too small. Don't make it too small, but don't make it very large also. I mean, it doesn't make sense. Okay, so let's do, so I'm doing something, let's say 50 by 60, or let's say 50 by 40, 60 by 40, right? So I'll finish the sketch, okay? And here I am getting, so I don't do extrude operation to do sheet metal. So I want to do something called flange, okay? Create flange. So I'll create this and I select this one, and it is going to make whatever sheet metal is there. How will it decide the thickness, right? So for that, there are some rules that are already added to Fusion, that depending on which the thicknesses of these things are calculated, right? So here, sheet metal rule. In this design, in the library, I have these few things. So I have steel and what kind of thickness, 2.5 mm thickness, K factor I've given, it's given in that rule. There are some bend conditions that are there and so on, right? So similarly, aluminium 2 mm thickness is that. Let me select this for the timing and say okay, right? Okay. Naturally it is 2 mm thick, right? I can see that by going to inspect, or I can, click on I as a shortcut and just see this, and this is 2 mm, right? I don't want 2 mm, I want 0.6 mm. So here on the modified tab, no, you have this icon which is sheet metal rules. So once you click that, you will get this tab which has these sheet metal rules. Okay, and in this design I am using the aluminium one, and it says edit rule or new rule. So instead of using the same rule, don't edit it, because it will change the settings that are already there in the system. So rather what I'll do is I'll click new rule, and it will say okay, new rule is being created, which is based on the aluminium, the data from aluminium millimeters. So I will call it something like, let me call it aluminium 0.5 mm demo. Okay, right? And now I've created this, but these details are not edited. So I can go ahead and edit rule, and I will say the thickness is 0.6, oh not 0.6, 0.6 mm, right? Now the K factor is slightly different, and it would depend on the type of material and the thicknesses that are there. So for the timing, I'll just put it 0.44, or rather I'll do 0.30, because that is what it is. But I want you to verify. I am putting a random number over it. Okay, so I want you to find out what is the K factor that you should use and put it in this set of rules. Okay, and meter, rib, sim, gap, just leave it as this. Bend condition, just leave it at this standard, whatever is there, and just say save. Okay, and close it. Okay, and here after I've made this new rule, I have to go and change it. So here it is still using the previous rule for making the sheet metals. So I'll click on this and I'll say this, and I'll say okay. And now as you can see, the sheet metal thickness reduced. Internally, uh, uh, the last assignment for this sem is to make a manufacturing theme YouTube video intro for the channel. Hey, that would be nice actually. Okay, anyway, so let's move on. So this is the sheet that is fine. So internally, in as a kind of information that is stored in this file is mostly just the sketch. It's just a sketch. There's no other operation. See, there's the sketch and there's a flanging operation. Now I can create other details that are needed. So I want to create a something that comes up like a box like this, right? So all the sides should come up. So I will select flange, and I will, let's say, select okay, one of these edges. So let's say this edge, this edge, this edge, and this edge. 4 edges I will select, because I want to make a covering. And or no, I'll not do this. Let's do, oh no, let's do that. Okay, sorry. So okay, so I'll select this. Okay, now I will just pull this up. See what happened when I pulled it up. Let me just give it a dimension, let's say 25 millimeter, and see what happened. So the software itself understands how the sheet metal designs should be made. So it gives you a fillet automatically. Okay, it will give you a bend radius which you have defined in the rule. Okay, and it will cut design this in a manner that is different. So I can change all these properties by going to, let's say, okay, modify sheet metal rules, and let me go here and edit this, and let's say bend radius is the thickness. Okay, so this is the radius is thickness. So I want divided by 2. I want a very small bend. I want a very sharp bend, divided by 2. Okay, or rather just say into sorry, bend conditions, thickness into 0.5. Okay, relief width, just leave it at that. You can change all of these properties to see what changes. Okay, corner conditions, let me go that to corner. So trim bead, I want to go for something like a rounded. Okay, and relief is okay, fine, thickness times 3. Okay, 3 bend radius, I will round it with radius. Okay, thickness. Okay, so see, things changed over here. Okay, this is the kind of relief hole that is there. So explore what are these various options in that rule book, and you will find out how it's done. Okay, now what do I want to do? Thicker, why does it seem thicker after the bend over here? uh, it's not, maybe it's like a visual thing, but it's not thicker because there's no thickness information other than what is set in the rules. Okay, so okay, so now this is done. If I want to make the second part, then I can't directly start modifying here. Okay, so I want to do something before that. So what I want to do is I want a U-shaped, not a U-shaped curve, but like a slightly differently. You will see what I mean. Okay, so what I want to do. Okay, so what I want is I want to cut some part over here. Okay, and I'll create a flange. No, I will. Okay, so what I will do is I will do something, go to modify and do this. So when I select this, I'm trying to unfold the whole thing and see how it looks unfolded. Okay, so I'll select the part which is stationary. So I want to select this face which is stationary, and the bends, unfold all bends, I will say, and this is what it looks like unbended. Okay, now on this surface I will create a sketch and I will cut out some part of it. Let me use this, and let's say I want to cut out this much. Okay, I don't want to finish sketch. Wait, don't finish sketch, edit sketch again, and I'll give it some dimensions. Let's say 5 mm, and let's say this is 20 mm. Right, finish sketch, and now I can select this and cut it right on one side through all. Just change the side, rather all, flip, right? So I cut through that. Okay, now I can go here, modify, and I'll click on okay, refold faces. Over here there's a button called refold faces, and I've refolded. Okay, this is how it looks like. Okay, now what I can do is I can sketch on this face. Let's say I want to sketch on this face. Okay, I'll sketch here and I want to see if this works. So I'll sketch here and I'll start off from this edge and I'll go like this, and I will go like this. Okay, I'll say this thing, I'll give it some dimension again, give it an angle from here to here, let's say 30 degrees. Okay, and this height is, let's say, 5 mm, and I want this to be just coincident to this, so this sketch is become black. That means it's fully defined. So now this is done, and I'll create a flange from this one. Okay, and when I push it, Oh, it didn't do. Give me a second. I think I made a mistake. Edit sketch instead of this one. I'll place over here, finish sketch, and let's see if it does it now. Ha. So it should do. I don't know what I'm doing wrong, but yeah, okay, I'll leave this up to you to explore. I also haven't gone through it too much, but I just know like the very basics. So okay. Oh, sorry. Sorry. I want to do this. Okay, here. Okay, so you need to think about how you'll approach it. Now I want to do 30 degrees. I can do 30 degrees. Okay, increase it to some dimension. From the side view I can see, and say, let's say, okay, that's fine. So from here again I'll do like this, but see there are a lot of these uh, settings over here, which if you change you will get like slightly different outcomes. Okay, so you think about and explore all of this. Okay. Why does it seem to be thicker after the bend? It's not thicker after the bend. Oh, I'm sorry. Okay, let's see. I want to undo a little bit. Okay, so I will undo all of these things. I'm sorry. I'll just undo and I'll come back here. Okay, so this one, I hope till here it was clear. So now I want to create like a flange which goes in on an angle. Okay, so I'm not putting any sketches. I'll just go to flanges. I'll select one of these edges. Okay, pull it and put it at 30 degrees, say 30. Okay, I can edit it after I've put in, so something like this. And now I will pull this up also. So I want to do this, but I want to do it like this. Okay, so let me do front. Right, so once I'm done, this flange is created and all of these details, how this thing would be there, how these cuts would be there, no, that is defined in this file. Okay, what are the corner options, what are the bend conditions, and all of this, what are the relief placements and all that. Okay, relief shape. Okay, here the bend conditions, the relief shape is straight. So let me edit that, and I'll say in the bend conditions the relief is round. Okay, when I do that, when I update, this is what happens, right? Okay, so yeah, now in sheet metal what happens is I have to create a second part by creating a new component. Now this is done. I'll create a new component and start off with the other uh, piece. Okay, so don't start making in this only. And this is how you have to make it. You have to make it using the sheet metal functionality in Fusion 360. Okay, so now I can start off. After this I'll just sketch over here, and let's say again similarly I'll make a box. Okay, and I'll ensure that this box is around this size, because so by doing something like this, collinear with this and this, right? So it's the exact same size. Now go to flange, add this. What are you doing? select this, select the flange, and select this. Sometimes it doesn't select all the necessary areas. Anyway, so this is done. Okay, so this is the flange that is created. Now I will create the cover of this box. I want to do it outside, so let me just first pull it. I want to do it outside, so I need to just see if there's some interference. Okay, there's some problem over here. It's too close, and I can kind of add it a little bit more. Okay, or I can just say it's from the outside, so that, yeah, so that's my, I will do 5 mm. Okay, so that's my box. Okay, now for you in the assignment, you need to have another part at least which is permanently joined, so you have to think about that. Okay, and the permanent joints that which you will create, it needs to be fastened with some way. It needs to be fastened, and that you can, so once this is done, I can save it, and now I can go to the simulation part of it, and I can do a drop test. Where on earth? Okay, so here there will be a lot of these tutorials. I don't have the time to go through it all. I suggest you look for videos which will tell you how to do it. If you can do it, till then I'll also probably try my hand at it and see where I make mistakes, so I can comment later on in the class. Okay, so that's about it. If you have any questions, then I can answer, and quit now. Okay, so that's about it. I'm already slightly late for my meeting, but I'll go join in slightly late. So that's about it. Thank you so much for being in this class. I hope you understood the assignment. You hope you understood the Fusion 360 short crash course. And yeah, let's see what you make. I'll be very interested in seeing how creatively you approach this assignment. Okay, yeah. Riveting will be considered permanent. It need not be welded. Okay, even doing a nut and bolt thing will be considered permanent. The user should not be able to remove it without any tool, or if the user needs a tool to remove it, it will be considered as a permanent joint. Okay, yeah. Thank you so much. Thank you everyone. Have fun with this thing. Tomorrow we'll do slightly different. I'll send you a mail what we will do tomorrow. Okay, yeah, have fun. Today was the shortest one, I think. Okay, yeah, see you guys later.